and that might be useful or relevant to you as you construct games. And after that, I am open to a little bit more of kind of a whatever, and we can start to vote on how we want to utilize these Wednesday classes.
What do we got? 2 more of them left? Is there 2 more left?
We're on
week
slide,
8.
we're on slide 69 of 94.
No, I meant how many Wednesdays?
Oh, yeah, there's so today will be lecture, tomorrow will be next week will be lecture, and the final week will be the day of our big presentation. I guess I should talk about that before we dive into this too much. So week 10 on that Wednesday is going to be, that's first of all the day that capstone presentations are. So I am working to incorporate all of our games into that capstone presentation. So a lot of you are also in capstone, but that's a 12 o'clock to 2 o'clock thing on that day. I unfortunately teach from 12 to 1, but I might be able to get away with canceling or moving that to be able to accommodate these presentations. So yeah, we'll basically just have some stations set up down on the first floor. That will also coincide with the capstone presentations. People can come up, play the games, and talk about what you did. I think it would be really cool if we had one person at that station during that entire 12 to 2 period. My plan after that, since that is the day of our class, is we would come from that back here and spend a short period of time taking what I'm hoping is going to be a very easy quiz / exam. And then I would like to begin the rest of day kind of party leading into the evening. It is up to people whether they want to spend the entire day here. I can't make you do that, but I think it would be really cool. My plan would be to incorporate some Magic the Gathering and some board games and we could bring things to pass the time until people get off work. And then we could have a party. I plan to do a better job of catering it this time so that there's more food available, it'll feel more like a culmination of everything that we've done. But we really have today and next week to cover content before I think that we've done everything that we can. So plan for today to do this, plan for next week. I don't fully know yet. I know that I have mentioned an interest in world building and looking into that. I'll see if I can briefly touch on that next week. I want to briefly go over A-star and genetic algorithms because both of those are frequently used in games as well for training. But that's basically what I have. Any spare time from there could be spent working on games. Thoughts on that plan? Does that seem reasonable to people?
So what were you saying about that?
So capstone presentations are from 12 to 2 on that Wednesday of week 10.
Do we need to have like a slide deck or something?
That would be, that's for the actual capstone course, not for this class, but we're gonna incorporate showing off our games into the environment where the capstone teams are showing off their projects.
Okay.
So yeah, we'll have individual stations with laptops there for people to come up and play your games. And if you're also in capstone, then you should probably spend most of your time at your capstone table. If you're not in capstone, then you could spend some time at your gaming dev table, or you could be moving back and forth depending on who's there, what's going on, and the like. But that's the plan for now. Is that's a 12 to 2 window for that, and then we do something kind of like we did before, something like a 5 to 8 in here afterwards for those who work and would like to come play games at that point. Obviously, that's a very long day where you would be doing something for this class from 12 to 8. So you do not have to do all of that if that doesn't make sense with your schedule. But to whatever extent you can and want to be involved, that would be awesome. Just getting a quick show of hands, maybe, who thinks they could be there for the 12 to 2 and man a game dev table? If I can't some compilers, for those who are doing compilers.
Oh, yeah, yes, absolutely.
So some people, that would be good, it's about one per group that's in here. Let's see, who would be able to be here from 5 to 8 in the evening, if that were offered as well, so about the same number of people. That would be awesome if we could get a reasonable number of people here to show off some games. And then who has interest in doing something, if we did something like a 2 to 3 o'clock quiz / exam, who would be interested in having some games happening in here, who would attend that from 3 to 5, something like that, will be set up and also just have some fun, who wanna attend that?
Honestly, it depends on how things in my other classes are looking.
Yeah.
If it's like, I would be happy to come here and show off the game, and I would like to come to the party, but if it's like. I got homework to do, or I really need to study for this test, that
Yeah.
takes.
Absolutely. Completely agree with you on that.
But what time slot was that, what day was that, 3 to 5?
Yeah, it's the Wednesday of week 10.
Oh, okay.
Because we will not have a final in here, basically we'd be done with the graded outcomes of the class, once the games are in and you're writing reviews over that week 10, there's nothing for finals week in the class. So hopefully that means this class is mostly dying out with its workload as everything else in your other classes are taking into higher gear. Hopefully. The reviews can be a little bit, but I'm excited because I think we have some really good games coming our way from what I see. So I'm gonna start going over some of this material. We should take some breaks as needed for sure. Make sure to advocate for those, and or we can just set times for them, something like maybe 3 and 3:40. Or we should get up and take a bit of a break. It's been a while since we talked about this. Who remembers temporal difference in the driving home example?
Kind of.
A couple people, somewhat. So Monte Carlo was this idea of we're gonna wait until the end of the episode, figure out how the episode went, and then back propagate that information through the episode. So we saw something like the actual outcome from this entire situation is that it took 43 minutes to get home. Some things were better than expected, some things were worse than expected, but regardless, the total time ended up being worse than we thought. It was predicted to take 40 minutes. Or sorry, predicted to take 30 minutes at the very beginning, and it took 43 minutes. So every prediction level at prediction point in time is gonna get shifted up toward the actual. Whereas with temporal difference, we shift it based not on the end result, but on the result of the guess from the next time point. So instead of it taking 43 minutes, leaving office to reach car, that took longer than expected because it was raining, because other reasons. So we see that the causality for this was likely something in here. So why increase the amount of time that you think it's gonna take to leave the office to reach the car just because it happened to be Friday? So this is a way of trying to get better correlation and or causation into this process. And as you train this, it will start to. It'll start to move closer to what's expected faster rather than waiting, which also means that you can learn while online. Instead of waiting for the episode to terminate and then have to think about what happened. At every single step, there's a small analysis point. How did this differ? How did this change my expectation of how long this is going to take? Back propagate that one step and now move this estimate towards this level. This change means that this should bump down. Even though this took 43 minutes, the reaching car to exiting highway, we saw that traffic was really good on the highway. So we're going to bump down the expectation based on the data that we got, that was the highway portion of this was faster than we expected it to be. The issue was that we got behind a truck on the secondary road and had to go at the truck's speed. With the actual outcome, we're punishing every one of these predictions based on the fact that we got behind a truck. instead of just the secondary road portion, which was the reason why it was so slow. So let's actually talk about advantages of using temporal difference over Monte Carlo. Versus the dynamic programming that we talked about, we still don't need the model. So it has the same pro that Monte Carlo had versus dynamic programming, in that we don't need the full model of the environment. We can operate based off of trained data, online data as we're gathering it. Versus Monte Carlo, this concept of online incremental learning. So while we're gathering the data, we're learning, but we're also updating based on every single data point, not waiting for the episode to end. How much did our estimate of the return change between two states? That's going to become the update to the prior state. We also don't need to ignore episodes that take experimental actions. Because Monte Carlo, we don't know, like the entire return that we get at the end of that is based on the entire history of decisions that we made up until that termination point. So if we take an experimental action early and it affects the entire rest of the run, then we're going to try to back propagate all of that back through Monte Carlo for every decision that was made, not just the exploratory action. Whereas with temporal difference, experimental actions might affect the next time step, but after that, it will stop affecting it quite as much. And we see an exponential decay on how much the experimental action ended up affecting the expected return at each of those middle points, if that makes sense. So we ended by looking at this example, where we start in state C, and we want to either get to the state left of A. When we do that, we get reward 0, or the state right of state E. When we do that, we get a reward of 1. We want to converge to the true state values of 1/6, 2/6, 3/6, 4/6, and 5/6. Ignore the first 1/6. So to do this, you can imagine that if you're using Monte Carlo, you have a really long run of some number of states that you visit until you eventually terminate. And then you're going to try to backtrack the value of whether you got to 1 or 2 or did you get here or did you get here? The value of that is going to be backtracked, reversed through the process that you follow. And we find that over time, so here is 0. We expect that we initialized everything to be 0.5. After one iteration, we find that when we find this last step, we just back propagated a single step back to B, and it doesn't matter anything about what we did before that point, because everything else has value 0. The reward of going left to right here is value 0. So you can imagine what happened was some run where we start here, we go 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 here, 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 there. Monte Carlo would try to back propagate all of this through every state that we visited, but temporal difference, since the value of everything that we visited throughout this entire run was 0, we're estimating that no change was made because we don't know the value of the terminating episode. When we finally get this real reward of 0, we back propagated a single step, and that's it. So it starts to slowly learn from there. On the next run, the estimates for the values of the states look like this. Everything else looks like 0.5, but now A looks a little bit worse because going left from there ended the episode last time. After 10 episodes, we see that this has fallen further. Sometimes we're in A and we go all the way right and end up winning. But we have learned that being in A is relatively bad comparatively. And we've learned that being in E is relatively good comparatively. After 100 episodes, you see that it's basically converged to these true values of how likely you are to end up at the state 1 based on this random walk. So given that you're in E, the chance that you end up here instead of there is 5/6. So you would expect that the value of this converges to 5/6. And it was really close. The error is minuscule. State D should be 4/6. Error pretty minuscule. State C should be 3/6, exactly 1/2, and it was really close to that. So within even 100 episodes of using temporal difference, we got quite close to those true values. Just by simulating and updating based on the state that we get to next and back propagating that. Another graph that might show how this works is that we can look at how Monte Carlo works with regards to the actual root mean squared error. So Monte Carlo is going to start with all of this. When we don't have much information, we start with random state values. So we expect that the error is going to be high, but the rate of learning at every point in time is going to be the slope of this. A high negative slope involves lots of learning. And you hope that all of that learning is front-loaded so that it becomes flat eventually. There's no more learning to do. So less slope says that we're learning slowly and still have high error at the end. Something like this learns slowly but has a really good final. Something like this learns really quickly but then struggles to take that last little step. And we'll actually talk about why this happens based on these alphas are learning rates. This says based on the new information, we actually talked about this in the first slide deck. Given a particular run, how much do we update our expected values of these states based on this last episode that occurred? So a high value of the learning rate is going to very quickly learn what good actions are, but then it's going to start overreacting to extreme examples. Because it does that overreacting, it has a hard time minimizing this error from here. It's kind of like you won the lottery once, so your expected value shoots way up. If your learning rate is high, then you're going to think that that win means that you're very likely to win the lottery, and it's going to take you a long time to learn not to do that. But that's actually a negative expected value gain. If you use a very small learning rate, then you're also going to learn, but not very much. You're not going to be able to learn from the good results. If you use a moderate learning rate, or sorry, even lower learning rate, then you get a better long-term projection, but it takes a longer time to learn those values. So you can imagine something like, what would be a good simulation? I really like the concept of going on dates because it's something that a lot of people do a lot of times because they just don't quite find the right match, the right environment for you. So you can imagine now having a particular learning rate associated with the information that you get from a particular date. If you have a really high learning rate and then you go on a date with a narcissist, you might not go on a date for 5 years just because you learned so much from that. It's like, you know what? Maybe I'm just better off being single for life. I don't know if I can interface with that. A really low learning rate, you'd have to go on a bunch of dates to gather any information. I had fun, I had fun, I had fun, I had fun. And with a really low learning rate, if you start out saying, I don't think I'm going to have fun, you need a ton of data in order to get to the point where you have information about what to expect. But once you get there, any ridiculously positive or negative experience won't shift your views very much. So you reach kind of a stabilization point that is, it takes longer to get there, but it has the best overall result, not reacting to extreme events. But we can see that in general, temporal difference learns faster and converges to lower error rates than Monte Carlo. So temporal difference is really useful. Questions on anything from these last couple of graphs or how to relate them to some example? All right. We'll talk about batch updating. So the idea of a batch is that you're going to throw the same example at the learner over and over and over and over again. This would be like going on the same first date with the same person over and over and over and over and over again. Wiping your memory each time, but then collecting all of the data and analyzing the data at the end of that. You don't need to know more than one person to do that. So you don't need very much data collected. But at the same time, you're going to very much bias yourself based on the kinds of experiences you have with that one person. So repeat learning from the same experience. Very good to do when you don't have very much data available. If data either is really expensive to collect or is just not that accessible, then you can use batch updating by throwing that same data at the learner. It's not as good as burying the data, but it's better than just training it once or twice and stopping. So if you have a very small learning rate, it will still guarantee that you will converge to some value. But do note that Monte Carlo and temporal difference converge differently based on the fact that they're waiting till the end of the episode to learn or learning at different points throughout the episode, whenever an action is made. Let's play a game. You're going to be the learner in this situation. So we have two states, A and B. You can either be in A or you can be in B. In the first episode, the first thing that happens is you find yourself selecting, so you do action, I think they're technically actions. You do A and you end up with 0. So you choose A and you get 0 as a result. But then after A, you choose B and get 0. And that terminates the episode. Now the episode has ended and you got a cumulative reward of 0. But you picked A and then you picked B. The next episode, you pick B is the first thing that you do and you get a reward of 1. And then you get a B and a 1, 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 and a B and a 0. And then you run out of time. If we wanted to figure out the value of selecting these actions, the value of selecting B seems to be 6 out of 8. On average, when you selected B and it terminated the episode, you got 6 total reward in 8 total episodes that you selected a B. So the value of B would be something like 6/8. The question I would have is, what is the value of A? You only ever selected A once. You got an immediate reward of 0. And it didn't terminate the episode. Is it 0? Is it undefined? There's a good solution to this. So basically, I'm actually going to erase this because this will show this a little bit better. We kind of have this experience. Sorry, was there an A in there? No, there wasn't. I think there's supposed to be an A and a 1 in there.
I think that A is just supposed to be a 0, probably.
Yeah. Yeah, it is supposed to be a 0. I love this book sometimes. So state A had 0 return in 1 episode. So you could assert the value of being in state A is 0. If we do this, then we minimize the mean squared error on this training set. Right? If these 8 episodes were used as training, then you would, by estimating the value to be 0. But imagine that what's happening in reality is closer to a Markov property, where now we're going to view it as something like this, where whenever we pick A, we immediately go to B, and now we choose the reward of B. With the 1 episode that we got, we saw that we went down this path. This is what's happening in reality. So whenever we pick B, 75% of the time we get 1, 25% of the time we get 0. Whenever we pick A, we immediately go to the reward of B. So we could use the knowledge of what we did when we got B, seeing that when we go to A, we then go to B. So we can now say that the value of A is equal to the value of B. Because of whenever you pick A, with probability 100, you go to the distribution of B. So that's what batch learning is doing, is it's trying to infer from data kind of some causality between some of these different distributions. Rather than using the direct data that you have, you can infer some of the connections between the variables and use the data that you collected just on B when you go from A to B. So you can use this to create this best fit model of a Markov process based on the training set, and you can generate a model that looks more like this. And in practice, we will find that a model that looks like this will be more predictive of data that you're going to see in the future, given that you only had 8 episodes. 8 episodes is tiny. There is no sample in 8 episodes that you can learn from. But if you say that the value of A is 0, how likely is that to be the case when we move forward? This is much more likely to be predictive of reality than the small piece of data that we got, if that makes sense. So we build a model that best represents the data that we saw. You can use batch with either temporal difference or Monte Carlo, but as we saw before, batch temporal difference tends to outperform batch Monte Carlo. So temporal difference is generally what's used in practice. So what we're about to do is probably go over the single two most important algorithms we've talked about so far in the class. You can throw a lot of problems at these algorithms, and they can do a lot for you. In fact, I would argue that if you're trying to do something really cool in this class, or you're trying to do a really cool project, using one of these algorithms is a phenomenal way to start. So the first one is called SARSA. Anyone heard of SARSA? It doesn't get too much attention, which is unfortunate because it's a really cool algorithm. It's a TD0 algorithm. It uses the on policy. Can someone remind me of what on policy versus off policy was about?
On policy, follows the directions of what it thinks is the batch. And then on policy, it takes random action.
Kind of.
Okay.
So on policy says that exploration is built into the policy. So we're always going to do what the policy tells us to do. The policy, when the policy tells us to explore, we're going to optimize given that we are exploring. It's like, given that I don't have a choice but to explore, I'm going to optimize knowing that with some probability, I'm going to be taking suboptimal actions. So for instance, to give the same kind of violent examples that I usually like to give for some reason, let's say I have two actions. The exploitative action is to stay here and continue lecturing. The exploratory action is to throw myself out that window.
Only the second or third, no, second floor. Wouldn't be
Yes.
that bad.
So maybe I'd be okay, assuming that I could break through the window and fall.
Good luck with that.
But imagine now that I'm preparing for making this decision. My policy that I'm going to learn through experience is that I should never do that. But if I follow an on-policy algorithm, I will know with some non-zero probability, I'm going to decide to do that. So I could prepare for this, and I will come to lecture wrapped in bubble wrap. Just in case I happen to make the decision to throw myself out the window. That seems kind of silly, but that's exactly how SARSA works. It's going to take into account the fact that it's going to be producing suboptimal actions because the exploration is built into the policy. I'm going to use a random number generator when I get to class, and if it hits a particular value, I'm going to throw myself out the window. Because I'm learning from that policy, every time I do that, I'm going to get a really negative reward, probably end up with a large hospital bill, possibly from some permanent brain damage. But I would be learning not to do that as I am doing now. But to protect myself from doing that, I can prepare in advance, knowing that that's the policy and I can't change the exploration of part of the policy. So to update, we just basically say that each step, we're going to use a learning rate. We're going to look at, so given that we've picked a particular state action pair, this is the value of the last state action pair. So as usual, we have some episode, and when we're in this state action pair, we've been in this state, there were some actions that we could have chosen, but we chose that action. And we're going to now see a reward as we move to the next state and then pick the next best action to do. So we're kind of in this position where we were here, we picked this action. We got to this state and now we're picking this action. So we're going from Q to Q, not from B to V. Remember that difference between V being the value of a state and Q being the value of a state action pair. So in the state, pick this action, ended up in this state, picked this action. Now we're pausing to go say, now we can backtrack and understand how good this pair was. Based on the reward that we got when we transitioned to this pair, this state action pair. So this is saying the new value of QST, STAT at time t, state t, action t. This is time t. This is time t plus 1. The new value of this is the old value of this plus some learning rate that we will pick times the reward that we got in this transition. The reward that we get at time t plus 1 plus our discount rate times this expected value of difference between here and there. So if this is a game, maybe from here, we think we have a 50% chance of winning. From here, we have a 75% chance of winning. By making this action from here, we dramatically increased our chance of winning by making that. The reward that we get here is additional. Maybe it's an extra turn that it took. But the idea is that we're going to find the difference, really just, you're going to think of this as the difference between the chance of winning at time t plus 1 and the chance of winning at time t. How much did this action improve your chances of winning or decrease your chances of winning? So this can either be positive or negative. You look at the reward that you got, you take this whole thing and you multiply it by a learning rate. If this whole thing is you won the lottery, then your expectation is going to shoot up. So this learning rate just says, how much are you going to prioritize every new data point that you get? Does that make sense? do we see how exploration is built into the policy? Or how we're utilizing the fact that the policy, there's nothing about the change in policy. If we make an exploratory action here, we're immediately accounting for it. We're not making any decision about knowing that this was an exploratory action. We're treating all potential actions as the same, exploratory or exploitative. So all this is the drive home example algorithm with an on-policy exploration. Or I guess we call it on-policy control. So pseudocode looks something like this. So we're going to take in, this calls it a step size, but I like to call it a learning rate. This is how much we're going to react to every new piece of data. If the learning rate is 1, we're going to throw away the entire history and take the last thing that happened as the ground truth. If the learning rate is 0, then no new information is going to change my views. Anything in between, we're going to take the history weighted as 1 minus alpha, and this new data point weighted as alpha. Does that make sense? So if our learning rate, if alpha is 0.05, then the entire history is weighted at 95%. And this time is weighted at 5%. And we just continue with this as we continue to learn more and more and more. The average that we've seen in history gets this weight, this time gets this weight. And we just move it up or down based on the old value. This value gets this much weight, and that's going to change the current expectation of the value of this state action pair. So we initialize every value, every state action pair in the entire problem to be some value, arbitrary. Then for every episode, we initialize the starting state. We need some way to determine where we're starting. So once we find the starting state for the episode, we then choose the action using the policy. So we use some policy derived from the action selection. We would either use epsilon greedy or UCB, any other type of policy that we have derived. We would pick an action based on that policy. For every step of the episode from there, we take the action that we selected here. We observe a reward, we observe a new state that tells us where are we now? Based on this action, how has the world changed? We then choose a new action from this new state using that policy. Once we've chosen that action, we then update according to the expression from the prior slide to get a new value of the estimate of the value of taking this action from the state that we selected here. Then we update the state that we're in to be the new state, the action that we took to be the new action, and loop back to the top. And we just continue this process that learns as we go. And it's always just looking one step backwards instead of waiting for the episode to terminate and then back propagating all of that information through the entire episode. So it's a surprisingly simple algorithm. It's not doing very much. Even though this looks gross, there's not that much in this expression. It's just saying we're going to take the difference between what we expected and what we observed, multiply it by the discount rate, add the reward that we got, multiply all of that by the learning rate, add it to the old expected value, and update. This becomes that 5% of what we just observed that we gained between going from the last state to this state, update it by 5%, and then add it to the old history value. Update the history value. Loop back around. Pick the next state in action. Do it again, pick the next state of action, do it again, until the episode terminates. Or forever, if it's a continuous problem. How are we doing? To what extent do we feel like we understand Sarsa? Question?
Maybe that's a question. How does the discount rate affect the derived state in action?
Yeah, it doesn't. So we're gonna pick this greedily. And then once we do, then we say based on the future, it's something like, where should I invest my money? Whatever it's gonna be worth next year, inflation is gonna be pretty consistent. So you should expect that how much money you have next year is how much money you have right now, times the interest that you're going to get. But then also divided by the interest rate, like divided by inflation, sorry. So that then you would get in today's dollars, is it worth putting your money here versus there? So, yeah, I like to think of it in terms of money, but yeah, the discount rate is just like an inflationary measure. It'll have a reinforcement learning agent beat you sooner if it can. We need some way to show if I can beat you in 2 turns, it's better than beating you in 4 turns. Let's give you another example of a game that we can play. Nice, simple game. It's called Windy Grid World. There is wind coming from the bottom of the world to the top of the world. So the agent makes a decision about where to move, left, right, up, or down. And wherever it moves, if it's in any of these columns with wind, whatever it decides to do, if it ends up there, it's pushed up by this value. So the agent here decided to move right, but this 1 pushed it up 1. Move right, pushed up 1. Move right, pushed up 1. This agent needs to learn to get to the goal over here. So to do this, it needs to get past the wind, go all the way down, and then move left in a way that is going to push it up to the goal. If that makes sense. There's actually no way to get to the goal from here. The wind will push you past the goal if you try to access it from the left. So you have to get at it from the right. So this is the kind of example that we use to trick a reinforcement learning agent. If there's only one way to terminate the episode, it's going to take a little while, but it needs to learn the path that minimizes the path cost of getting there. It can't spin its wheels for a long time trying to find the goal and expect a high reward. So the reward is -1 until it gets to the goal. So it will get a better reward if it gets there faster rather than slower. So Monte Carlo, you can imagine, is pretty difficult in this environment because you have to wait for an episode to terminate, and it might terminate after 1,000 steps or more than that. So it becomes really hard to learn this action because it's never going to prioritize learning that, back propagating this all the way through the episode every single time with some exponential decay applied to every step. That's going to be really tough to learn. But with temporal difference, it's actually much better and faster at converging to this. Because Sarsa uses an exploring policy, it ends up finding a 17-step optimal procedure. But you can see how long it takes for a single episode to terminate the very first time. It's just exploring randomly, and it doesn't terminate the first episode until after 2,000 steps. But from there, it starts to learn how to do it. And the slope of this line says how efficient it is at finding the goal. It had a lot of exploring to do to find things, but because it was using temporal difference instead of Monte Carlo, it was actually able to learn it after a few thousand time steps. And by here, it's pretty much converged, found this 17-step process, and is exploiting it as much as it can. I will show you an example of this once we talk about the other algorithm. So. What was off policy? We talked about on policy as exploration being built into. The learner. What's off policy?
We start out exploring and then we try to optimize it after we.
Somewhat. How many policies did we have?
Policy, then the greedy policy.
We did have two policies. What were they? Those were types of policies that we could use. But we had a behavior policy that we followed, and then we had a target policy that we were learning. So behavior and target are the two main words we were looking for. So behavior policy is what we are doing, target policy is what we are learning. To go back to the example of throwing myself out the window, because apparently I can't get enough of that. I would be, instead of rolling a random number generator, when I come to class, I would still be rolling that random number generator and doing what it tells me, but at the same time, I would be learning and thinking about with what probability should I be throwing myself out the window. I would like to never throw myself out the window because it doesn't seem to ever do anything for me. But what I'm actually doing to make sure that throwing myself out the window doesn't accidentally win me the lottery, I will continue to do it as an exploratory action. Will I learn that I should never do it? So there's what you do, and there's what you think you should do. And you will apply what you do to learn what you think you should do until you go online and you switch over to what you should do. So off policy often has a really good in practice performance. So Q learning is the off policy temporal difference algorithm. Who's heard of Q learning? Nope. Man, this one's much more popular than SAR, so this one usually has a hand or two. But Q learning is one of the most widely used algorithms in machine learning. It is the most widely used algorithm in reinforcement learning. So it's going to directly approximate the best policy, even though it's following a separate behavior policy. So what it does and what it's learning are two separate things. By making mistakes, I'm learning what to do to avoid making mistakes. So the difference between SARSA and Q learning is now, instead of using the action selection algorithm like epsilon soft, epsilon greedy, UCB, instead we're going to greedily pick this action. We're going to update the value of the current state based on what we should have done and not what we did, which is really interesting to think about. So let's come up with a situation. I wake up and it's the first thing in the morning. I want two actions that I can do, one that is a good action and one that is a bad action. What is the first thing that I can do in the morning that would be a good action? Brushing your teeth. Great, that seems productive. So I'm going to say brushing teeth goes over here. What's a bad action?
Go back to sleep.
Yeah, I like that one. Back to sleep.
The episode now.
I'm just going to leave that as a question mark. So let's say after I brush my teeth, what is something that is good that I could do and bad that I could do?
I get dressed,
All right, get dressed. I like that. That's pretty productive. What's something bad that I could do after brushing my teeth?
drink orange juice.
Yeah, you could. That's something that's worse, something that's obviously questionable. Right after brushing your teeth, you
Not your face for frying pan.
smash your face into a frying pan. I like that. You brush your teeth to make them nice and clean, and you're gonna knock them out of your mouth. Yes, lose teeth. Very questionable. From going back to sleep, what's the next choice you could make? You're asleep. You could wake up in a panic and try to make up for everything that you've done. So you could, I don't know. Rush, we'll call that rush to get ready, or you could continue sleeping. So the idea would be that what we want to do is something that is productive. But if we don't know and we want to play around with, if I actually go back to sleep, will I be so much more rested that even though I go through the stress of rushing, the total reward that I get from this branch is better than if I woke up and had a lazier morning and had less stress? Maybe, I don't know yet. But the update that we do in Q learning, since we don't build behavior into a policy, if I choose to go back to sleep, that's the action choice that I make. Since I know that this is the better choice to make, when I do this, I'm gonna update this value based on this value instead of that value. That seems really strange to do. But the next piece of experience we're going to get is going to be to update the value of this node based on which action we take here. So if we take this action here, then we're gonna update this in a way that may push this up to be better than this optimal. Therefore, this star moves over here. So you can see that once you make this action, by exploring, you're not incorporating the exploration that you do here as you figure out how good it is to make this decision or that decision. So your bad decision here doesn't affect this until this decision seems like it's better than that decision. Which is really intriguing to think about. You need two policies. The probability you're going to take a suboptimal action rather than the optimal action. But at the same time, you're learning this based on, you're not biasing this value based on the bad actions that you take. You recognize immediately that it was a bad action. And you say, I'm not going to learn from this unless this turns out to be really good. But I'm still going to go down this route because I need to know, I need to have more experience with this mistake to be sure that it's a mistake. So once a quarter, I'm just going to sleep in until 5 minutes before class starts. Wake up in a panic, get ready to go. And once a quarter, I'm just going to get that experience. And maybe by my senior year, I'll have determined that that's actually better than waking up and having a no stress morning. I just get more sleep, I perform better throughout the day, even if I'm 10 minutes late to class. I am a good every day. So your algorithm treats this as optimal. Maybe it is. But that's the off-policy learner, is what it does is different from what it learns. Two different policies. So here's Q learning pseudocode. It's exactly the same as SARSA, except that the update that happens is based on the maximum value action instead of the selected action. And that's used to update the old state. This really brings it into perspective, what the difference between SARSA and Q learning is. So here is another fun game where here's the start and the goal is to get to the goal. However, there is a massive cliff in between you and the goal. You need to walk around the cliff. The question is, how close are you willing to be to the cliff? Imagine that you, the AI, are following a policy where there is exploration. And the exploration is built into that policy and you are listening to it. So you're walking right along the cliff like this, and all of a sudden, your algorithm, your policy says, turn right and take a jump. You know that the right answer is to go straight, but there's an exploration aspect to this that says, at every one of these states, as you're going Optimal is forward. Exploring action is right. You have to not choose right here and 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 here before you go to the goal. So if the chance of taking that exploratory action and jumping off the cliff was 10%, then the probability of getting to the goal is 0.9, the chance that you're not making that exploratory action, times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 10. What is the value of 0.9 to the 10? This would be the probability of actually reaching the goal. If you're doing that. Someone type that in real quick. Point nine to the 10th? Yes,
0.348667.
about 1/3 of the time. So you would reach the goal and not make an exploratory action jumping off the cliff about 1/3 of the time if you were walking right along the cliff. This is why SARSA takes this safer path. Because exploration is built into the policy. Even though the policy is always saying go straight, occasionally, quite frequently, 2/3 of the time, at some point along that, you're just gonna say, you know what, I'm done going toward the goal. I'm gonna make an exploratory action and jump off the cliff. And because of the multiplicative nature of that exploratory action, you don't actually reach the goal very frequently. Whereas you can imagine now knowing that I'm operating on an algorithm that's going to have me doing some exploratory actions. Instead, I'm going to get the hell away from the cliff and walk as far away from the cliff as I possibly can so that my exploratory actions can't make me fall off the cliff. Even if you take an exploratory action from here, it's likely that you're going to recover from that before making exploratory action, and falling off the cliff. So this is why when you have a policy that you can't believe in, it's better to take the precautions to make sure that you can't get screwed over by an exploratory action. I like to think this is how something like an alcoholic should behave. Walking right alongside the cliff is, I've been an Alcoholics Anonymous for 3 years. I can stare at this beer right in my hand and say no. That's walking right alongside the cliff. It's really easy for that personality to crack under that pressure. A step away from that would be like, it's out of sight. Step 3 is, it's not in the house. It's harder to make an exploratory action because you have to decide, go to the store and buy alcohol, see the alcohol, drink the alcohol in order for you to fall off the alcohol cliff. I don't know why I picked that as an example. Off the top of my head. On the other hand, the real optimal path for this, what minimizes the number of steps that it takes to get from the start to the goal, is if you could believe in the algorithm that you are using. Q-learning is going to learn this red path. How is it going to learn this red path? By falling off the cliff a bunch of times. Instead of, when this happens to take this exploratory action and fall off the cliff, instead of backtracking this -100 reward to this state, we don't want this to affect that very much. We instead say, well, optimally, we would have gone forwards. So instead, I'm going to backtrack this to there. Even though I took this exploratory action, I thought it was going to be bad. It was bad, but I don't want to learn from the fact that it was bad because it wasn't what I wanted to do. I still need to do this in case that if I jumped off the cliff exactly right here, instead of a 1,000-foot drop, there's a 6-inch drop onto a pile of gold. You don't know that unless you take that exploratory action. So it's worth doing to learn from, but if the result is bad, I should have learned from what I would have done instead of what I did. Once you find this massive pot of gold right here, then instead of choosing to do this, you will then choose to do this because this now looks better than that. But since there is no pile of gold and that was all just an example, then we still get a large number of samples of jumping off the cliff, but we learn that we don't want to do that. So we switch from when we were learning to when we were performing, we learn this path. And then when it comes time to perform, we stop exploring completely. And we've now learned to take this path. So again, that's the difference between an on-policy environment and an off-policy environment, or I guess control. And we get SARSA and we get Q-learning. So we see the sum of the rewards. This is kind of a plot of how much reward we get. SARSA outperforms Q-learning in terms of the actual rewards that it gets during training. Why? Why does SARSA look like it's performing better?
Doesn't go to the cliff as much.
Yeah, it learns that safer path, so it gets to the goal much more frequently as it is training. But you don't have to turn off the behavior policy and follow the target policy at the end of it. You've learned one policy, the policy to go do in practice. Q-learning jumps off the cliff a bunch, but as it does so, it learns how to optimally get from the start to the goal. How are we doing? Does that make sense?
Hey, maybe we should take a break in 3 minutes.
Yes, we should take a break. I think we said 3 o'clock and it's past 3 o'clock now. So let's take a break. Let's come back at, heck, why not? Let's say 3:20. Let's give us a little bit of a break. We will come back in 13 minutes. All right. So I want to show a visualizer for Q-learning, just kind of to see how it works. This is a game that we're going to be able to customize a little bit. You can see the values of each of these cells. It's going to get a -1 penalty for every action that it takes. But it's going to start understanding how to update the value based on this. So somewhere in this grid, there is going to be a goal that it's trying to get to. Where do we want that to be? I want to do this 3 times. I want there to be an easy thing for it to learn, a moderate thing for it to learn, a difficult thing for it to learn.
Top left.
Top left. All right. A death cell is what they call it. It's a cell that ends the reward with a bad score.
Bottom right.
Bottom right.
Yeah, that seems pretty easy. You can't really have a problem with that. Where are we starting from?
Top right.
Top right.
Top right, all right, so here is there. Now we can make some obstacles. Where would we like to build some either walls or basically impassable cells? Turn cells into something that's impassable.
Bottom left.
So we can't go there. Where else?
Column 4, row 3.
So we could do something that makes it really hard for it to,
Or in the very center.
Yeah.
so something like
Bigger one.
here-ish.
Or,
You're off by 1.
yeah, up there one.
No.
0 indexed, gotcha.
Right there, yeah.
Those two.
Those two.
These two as well?
Yeah,
And then get rid of the ones on the left there.
Yeah.
yeah.
Can't seem to do that in this.
Okay, do the one on the right.
Yeah.
Yeah, these two as
Make it
well.
stretchable.
Okay, this seems like it should be pretty easy to learn, right? I mean, left, go left. Go left to win, go down to lose, is basically this game. But the policy that we're gonna start with is a random policy. So it's going to it has no idea what it's doing until it either wins the game or loses the game. And then based on the experience that it has from there, it's gonna be able to back propagate and learn on the fly in real time. So I'm gonna start with speed relatively slow, and now it is coming up with estimates for values of cells as it runs around randomly.
Oh.
We need to terminate the episode in order for any of these values to be anything but 0.
Or it goes almost immediately right to its down to its.
Hey, it got there. And now it's moving around, and you can see that if it hasn't won or gotten to something in a while, you can see that it's starting to build a model of how good each state is based on some kind of reward / discount factor.
Really going that right.
It is. So we're gonna speed it up a little bit. It's not learning too much because now it's basically converged for most of these cells what their actual value is, given that it hasn't lost an episode yet.
Not much to lose.
This is not, yeah.
It still hasn't hit this cell over here ever.
It's getting darker green, wait, lighter
No,
green.
it's hit it once.
Yeah.
It just hasn't. hit-
Yeah, since it won the game.
The last row.
Yeah,
But there we go.
hey, we finally hit it.
It smells movement.
And
Oh,
Yeah, never mind. Faster.
faster, faster, faster.
I already.
It's built a very good map of this, given that it can never lose the game.
It's just good.
But note that what it's learning is based on the optimal move that it should make, not the move that it's actually making. Which is why it's actually done a really good job so far of coming up with actual values for winning the game. It's using a random behavior policy, but it's learning based on what it should be doing.
I think we might have made a mistake by putting it in the corner.
Yes.
Because it only has 2 paths that go to that space.
Yep.
Or it hit the corner.
Yeah.
Seems like a Windows DVD logo. I swear it's off.
Maybe it is, maybe it terminates and is 0. I'm guessing there's a bug here as well, because the color of these 2.64s are different.
Yeah, the
Excuse me,
point
sir.
0.64 should be same colors, I assume.
Yeah.
Consider your API needs to update.
If
You can see, once it terminates an episode, it learns really quickly. And you can also imagine that if we stopped this process and now said exploit, then it would beeline for the terminating green cell in the top left. Because given that you're in any particular one of these cells, you would always want to move in the greedy direction, greedy direction, greedy direction, greedy direction, there. Greedy directions immediately beelines you for or toward that solution. But what it's doing is exploring randomly so that you get an infinite amount of information. In case maybe there is some cell, maybe this cell, when you hit it 1 out of 1,000,000 times, gives you a massive reward. If you didn't explore infinitely and just always beeline for the solution, you would never uncover that. But by exploring infinitely, you gather more and more and more and more and more data about this in a way that once you stop and exploit, you utilize the best knowledge that you've gained so far. You can imagine some games that are really hard to learn. Like, let's choose a reward cell. Choose a death cell. Let's choose a starting cell, and then we'll make some obstacles.
Oh.
Gonna make it really, really try to find that death cell, huh?
I mean, something like that is gonna be pretty difficult to learn, and in fact,
Idiot driver wins.
if you do something like this, it's going to, I'm just gonna turn this up to see that there is no path to this that is going to ever work. Because you have to make, here you have a branch where you have to make the right choice. It's a random walk of length massive. You have to find that one path and then make a bunch of right decisions in a row. With probability 50%, 50%, 50%, 50%, 50%. This is going to be 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Given that it finds this cell, only 1/22 of the time is it going to reach this cell, and then half the time it's going to make the wrong choice from there. So you can set up a really difficult problem for an AI to solve and learn based on the constraints that it takes to end the episode. I could leave this running for quite some time. And it won't terminate this episode one way or the other.
I believe in it.
That's about a 1 in 4 million chance of making it better, I think.
I think it's better than that because it's a random walk. It would be the case if when it stopped on a path and made a wrong choice, it had to reset. If it did that, then it would be multiplied. Cool.
On camera too.
I'll take it. That was impressive.
Go.
I believe you won.
But you can also see that because it's so far removed from this, if we had to restart the episode, it would be really difficult to learn what the process is, and this is why Monte Carlo is so bad. Is because this is a multiplicative 0.8. So in order to go from the start cell, if every time it hit one of these, it ended the episode and then had to back propagate this all the way through the path that it took, all the way to the end, how do we know which of these decisions to make? They're so far removed from a possible end of an episode that the discount rate times the discount rate times the discount rate times the discount rate times the discount rate, all the way back to the beginning of the episode has such a small overall value that it's really hard to learn, and you would need to get there so many times in order to have a realistic view of what that value is, that it's really challenging.
I don't think there's enough decimal display on this.
Yes, but even if there were, it seems like it would be challenging to learn.
Yeah, definitely not enough difficult.
Who do I want to give it?
It's been forever, I think, wouldn't it?
So basically, this is how Q-learning works. It uses the off policy, random policy to learn from, and then it optimizes based on what it should have done rather than what it does. Questions on that? Questions on how SARSA would have behaved differently? How would SARSA have behaved differently? Going to use the same exploration policy that it's going to learn from. So instead of when we had a goal over here, when it was close and it went there, it would learn that. But if it went here instead, it would update this value based on what it did and not what it should have done. So you can see that that helped it terminate a lot faster with those values that didn't rely on the exact experience that it was making. So this is why Q-learning is the single most used reinforcement learning algorithm, is it's the most versatile. So that's kind of where I want to stop things for reinforcement learning, I think. that covers most of the main algorithms and some cases of where you might want to use them. So I think we're gonna spend the rest of the time working on games and or I can answer some of the questions that I've heard around the class. I haven't been able to prioritize this class in office hours because compilers is a lot. So I will try to prioritize this class for the rest of today.